All right.
Brief introduction, my name is Hon. I'm the co-founder of Clinic Cloud. We're now called CC Labs. We do a lot of machine learning in the business, primarily in medical data. So I've been dabbling a lot with machine learning for a while, and I thought it'd be very interesting to see what we can do with CoreML particularly. I think I did one talk about CoreML immediately after DevDub because I was really excited about it. I've been playing around, and since then there's been a lot of very interesting developments. So I guess one of the big highlights is that TensorFlow is now fully supported using TensorFlow Lite. It converts down to CoreML. Along with TensorFlow, there's also a lot of big players like Facebook coming in with PyTorch, Microsoft as well with CNTK, having support for ONNX, which is the neural net compiler, and now you're able to build very interesting machine learning, deep learning models using a whole variety of frameworks. So given that this is a bit of a weird area where it straddles data science, a bit of iOS, Mac programming, and there's a bit of Python and some stuff. So I just wanted to get a feel of things. Who here has actually dabbled in CoreML? All right, and who here has actually built neural nets and played around with deep learning models? Cool, all right, so... all right, so given that that's not that many hands, I'll try to go as much as I can. There's a lot, so let's whiz through it. So topics to be covered: background in natural language processing, word embeddings, recurrent neural networks, Keras, TensorFlow, CoreML, and I might give a brief peek of the automated workflow that we've built for Android and iOS using Python templating. So first up, what is natural language processing? So NLP is a process of having machines understand language. The best example is Siri. So when you talk to Siri, you're not speaking machine language. You're not saying in a very structured way, hey, play music, I want genre jazz, Louis Armstrong, year of 1967. We're saying it in a very naturalistic way, which is playing a jazz song from Louis Armstrong. Now, the problem with language, especially in languages, very ambiguous languages like English, is that there are lots of different ways of saying things, and not necessarily all of them will convert. And so writing regular expressions to do all of this would be a nightmare. So this is where machine learning comes in, where you feed a lot of examples and you try to get the machine to parse out the structure of the data, right? Because after all, in lots of data, we'll find interesting architectures, interesting patterns that we can then architect machine learning models to then parse. So iOS 11 has built-in natural language processing. Some of you may have already played with it using the NS Linguistic Tagger class for tokenization, lemmonization. So for those of you who are not familiar, tokenization is when you give it a string. So the cat sat on the mat, and it then passes it and creates tokens. Tokens are individual words. So the cat sat on the mat are each individual words. Lemmatization is when you give it a word like, say, running, and you say, give me the stem of the word, and it'd be run or swimming. Swam became swim, or swimming became swim. So that way, you can have all the variations of past, present, future tense and such, but they all mean the same thing if you don't really care about time. So lemmonization is very good for that. What I'm going to be talking about is what we've developed using CoreML for intent classification and slot tagging. Intent classification and slot tagging is a method that's currently being used by a lot of vendors. So Siri uses that for parsing out that sentence there, playing me a jazz song from Louis Armstrong from 1967. Cortana does that for Microsoft, Alexa, and I think Google Assistant as well. They all use the same technique, which is essentially saying, if I give you a string of text, say, play me a jazz song from that, I want you to tell me, what is this thing actually wanting me to do? That's the first step, which is the intent. And then once we have the intent, we can then go down further and say, given this intent, what information can I extract from this? And what you want to do is you want to end up with a JSON or some sort of structured text that says the extracted entities are genre jazz, artist Louis Armstrong in the year 1967. So let's move on. So a lot of people would say, well, why do you want to do this on mobile? And this is an argument that's, it applies to all of CoreML and edge inference. So the pros of doing it on the edge is privacy. no data leaves the device, doesn't go to the cloud, no one's peeking at it and trying to like sell you ads. Cost, you as an indie developer or anybody don't actually have to pay Amazon or Microsoft, credits or whatever to actually run these algorithms. Availability, well, if you go outside of coverage and you go into places with 2G, you still can run this stuff offline. So that's an advantage of that. And speed, well, if you're in 2G area, then you're going to have slow speed, so running on device is going to be good. The downside is flexibility, and I'll talk a little bit about that going further. The flexibility that comes with building on devices is limited. You can't change models, and we know with machine learning, you're always trying to update it with new data, new model architectures, new hyperparameters that you've then built. Memory, that's a really big issue. So I'll talk about word embeddings coming up, but word embeddings take a lot of memory. There have been attempts to what's called quantize them, which is reduce weights from float 64 down to int 8s and try to maintain accuracy. But that's still really a big challenge at the moment. Compute. So when you're doing these processes, they do a lot of compute. And so it drains the battery life. And difficulty. It's rather more difficult to actually try to get it to work on the edge. So the first step in any machine learning process is data vectorization. When I say data vectorization is, if given some piece of data, how do I turn this into a vector? Because a vector is what we feed into machine learning models. It's really important. I cannot stress this any further because there is a mantra in machine learning which is garbage in is garbage out. If you don't feed it the right data and you end up with really bad results, the best thing to really do, two things if you're doing deep learning, is A, lower the learning rate, and B, check your data. So saying that, things such as images are naturally very good as vectors. In this case, they're actually tensors. So when we talk in machine learning land and in math, we go by hierarchy. So a vector is like your arrays, right? So a vector is an array. A matrix is an array within an array. So that's a two-dimensional vector. And then when we talk about tensors, we talk about ranks. So we talk about third rank, fourth rank, fifth rank, which would essentially be, if you look at this thing, a construct like an array of an array within an array and an array. So it keeps getting embedded inside itself. So here's the really interesting question. How do we deal with words? How do we vectorize that? And I'm going to show you two ways. The first way, which is really simple, is what we call one-hot encoding. So one-hot encoding is what we call a sparse representation. Sparse because it takes up a lot of space. So if I had this word, hello world Taylor Swift, nope, right? What we do is we say there are like 1, 2, 3, 4, 5 words, so therefore it's going to be a vector of size 5, and each time, each spot in that vector, I'm going to put a 1 in it. The problem with that is if you have a very large corpus of words, let's say 6 billion tokens, like what, no, actually no, 6 billion is a bit too much. So let's say 250 million, which is what Wikipedia kind of has. You're going to have a 250 million row by 250 million column matrix. And these are all floats, so you can do the math and your memory just explodes. So word embeddings is a solution to try what we do to densify the vectors. And what makes a good word embedding? Good word embeddings are ones that actually capture the meaning of the words, and we call this semantic representation. An example of semantic representation is in this graph. I'm sorry if you can't really read it or see it, but what it's actually saying is, say, if in a very high dimensional space, I took the word king, and I looked for the word man. If I drew a vector directly from man to king, and then took that vector and transposed it to the word woman, it should point to queen, because it should learn the representations that man is to king, woman is to queen, and so on and so forth. So there are numerous ways of doing it, lots of different techniques. The most commonly known and most famous is word-to-vec, which is what's called a skip-gram model. So given the last 3 words of a sentence, I want you to predict me the next word. And then you have a bag of words and glob and so forth. But what's really interesting is that by doing this exercise of saying, given the last 3 words, I want you to predict the next word, the model learns that certain words are closely associated with each other. So you can say things like, all right, I'm going to give you an analogy. Melbourne is to Australia as to something in Germany, and it might come up with Munich. even though no one explicitly said that Munich is in Germany. Okay, so moving on, artificial neural networks. Artificial neural networks is going to be one of the topics of this talk, is a way of doing machine learning and deep learning. It's probably the best at the moment, but there are lots of different ways of doing machine learning, as support vector machines, k-nearest neighbors, but this has been the one that's given a lot of promise. So word embeddings like fast text and glove and word2vec are also built using artificial neural networks. And when people talk about deep learning, don't be fazed by it. What it really means is that there are multiple layers in the neural net. So that's just a fancy way of saying it's really complex. Once you look at it, actually, it's actually really simple. So what a artificial neural network actually is a linear regression model or logistic regression model with a nonlinear function applied to it. So what gives artificial neural networks such good representational power is this nonlinear function. So I promise this is the only maths you'll see in this talk. So given like x1, x2, x3 as inputs, as numbers, I want to calculate the sum of the product of that, and then I apply a function that says this is either on or off. But you don't have to worry about that because a lot of the frameworks take care of that for you now. So moving on to recurrent neural networks. So there are a lot of different ways of putting together neural nets. And just think of it as Lego. You have all these blocks. You could make a castle. You could make a Millennium Falcon, whatever you want to do with it. And neural nets are pretty much the same thing. So when we talk about convolutional neural nets, it's essentially a way of piecing together all the neurons to look at the data in a certain way. So there is a family of neural network architectures called recurrent neural networks that are very good at sequential processes. So what I mean sequential is that you have a time step of -1, 0, and 1, and you want to predict the next thing, or you want to actually classify a sequence. So the reason why is because they have what's called memory. So it knows what happened in the past, so therefore it can predict the future. The problem with recurrent neural networks, which is the grandfather of all of this, which is that first graph here, is that there's a problem of the vanishing gradient. So in neural nets, we follow the gradient through stochastic gradient descent to end up with a minimal point to get the best prediction. The issue with recurrent neural nets is that if you take, a good example is if you took a tangent and you took a tangent of the tangent and then more of the tangent, you end up with just a flat line. So what we do as tricks to do it, to fix this vanishing gradient problem, is what we call the long short-term memory cell, or the gated recurrent units that have specific units in here. You probably can't see it, but these are forget gates. So as the data flows through, the neural net decides whether I want to keep this or I want to forget it, so therefore it doesn't accumulate too many gradients. Don't have to worry too much about this because Keras takes care of this for you. So I just want to talk about the model, the framework that we've built. Essentially, we built a React web app that connects to a TensorFlow training server. We have a fast text word embedding that we pull the embedding words. We then train a model and store that into a Google Cloud bucket. We have the same web app as it runs, pull the model from that, and we send it to, in the case of Android, we have a Docker image that runs in Google Cloud that builds the project using Gradle, and an iOS build server that runs on Mac Stadium that runs a Flask server that has a continuous queue that pulls jobs and builds the framework. So fast text word embedding. So fast text word embeddings were chosen because it's currently the state of the art. It gives very good semantic representation. We used a pre-trained gigawords corpus, about 6 billion tokens that's been trained on. It takes about 8 gigabytes worth of RAM, so this is the problem why you can't really run all of it on your phone. And so what we did was, as a hack, was we took each word that we use in our training corpus and we did a Euclidean distance search, essentially saying if I had this word, find the 1,000 closest words in that space. And then we added that into a SQLite database of 300 number vector. So once we had that, we are able to train the model in Keras, using Keras on TensorFlow. The reason why you want to be training using these semantic representation word embeddings is that it already captures a lot of meanings in the word. So if it sees, for instance, the word coffee in the same space as, say, the word tea, then what that means is, these words are very similar and highly related, so therefore I will tag it in the same tag. So going on with Keras, Keras is for those of you who never played, is a high-level abstraction over multiple backends. So it supports TensorFlow, Theano, CNTK, and I think AmexNet right now. The cool thing is that it's CoreML compatible. So the team at CoreML have worked really hard to make sure that most of Keras is working with it. There are some caveats such as recurrent neural network paddings, but there are ways of going around it. So the best thing is that it also has TensorFlow has very good Android support. So the workflow that I would highly suggest is if anyone's trying to build machine learning models is to use Keras on TensorFlow, build it for CoreML for iOS, and then take the model, convert it into TensorFlow, and run it on TensorFlow for Android. So CoreML, going really quickly, is the team at Apple have tried really hard to make sure that the transition from data science to iOS and Mac is as seamless as possible. So they actually modeled it after NumPy. NumPy, for those of you who never played, is a numerical analysis tool for matrix multiplication and very fast maths. Now the crucial thing, if you guys are really interested about CoreML, the only thing you really have to know is ML multi-array. That is the most important class in the entire framework. If you know how to manipulate ML multi-array, you're flying. You can do anything with this stuff. And converting CoreML is so simple. It's just a single line of code. Now, there is a caveat again. CoreML is statically compiled. So you need to know beforehand what your inputs are, what your outputs are like, and the whole names of your processing flow, which is a problem because I'll come to that now. So this is Python code. So this is essentially a snippet of Keras. Keras is a way of defining a model of how I want to do things. In this one, it's essentially a sequential model. So I'm saying I want an LSTM, which is a long short-term memory cell that takes. So what's really interesting, if you look at the red area, input shape of none and 300. What I'm saying here is that I want Keras via TensorFlow to, at training time, not runtime, training time, determine the length of my sequence. And then each token, each vector is about 300 numbers long. So that's important. The second most important thing is that other one that I've highlighted, which is the number of labels, right? Because what happens is that at the output neuron, the output neuron is going to say, well, there are 6 things I want to classify, so therefore I will only have 6 neurons. So you need to know those are the 2 most important things: what the shape of my input is and what the output number is going to be like. It's really easy to do this in Python land because it's dynamic and you can just pass the arguments through. But again, as I said, CoreML is statically compiled. So that's a potential problem. However, remember I said CoreML models are statically compiled, but if you can manipulate ML multi-arrays, anything is possible. So this is going to freak out some people, but what we actually reverted to was Ginger templating, which for those of you from PHP land, maybe Ruby on Rails, whatever, are very familiar with the concept of templating. So what we do is, at the end of the training phase, we look at our model and we say, all right, what is it that we had output? So for something like that, we say, all right, we have a type that is an intent classifier, the name is the utterance intent, and so the intents that we expect are make, whether, news, recommend, and help. So those are 5, so we can quantify the 5 of them and they're in order. The order is really important because that's how you train it. And then we say in iOS, we have a file name called the something.ml model that we're going to include. And then the 3 most important things, which is the input operation name, the output operation name, and the input shape, right? So what we do with that is we look at that JSON, we write some Python code and do some templating. So we say, all right, input shape is 300 here. We have a template, Objective-C, unfortunately. We have a template in Objective-C that takes the input shape that we have in the config and then writes it in. So what happens is that we have a whole bunch of H&M files that are correct for the ML model. And then what we do is we take Xcode Jen. I don't know if anyone's played with Xcode Jen, but it's pretty cool. So what we do is when we do the fast text training, we also get a SQLite database back with all the vectors. We take the SQLite database, we take the H&M file and the ML model, and we smash them together to get as a Xcode project that we then use Xcode build to get a framework. And then what we do with that is we put it into an app. I don't know if we have time for demo, but...
We've got time for demo.
Okay, cool. All right, so so this is the web app that we kind of developed-ish. So and we have a pre-trained model here. So in this we have, say, coffee, and we have entities. So we have drink, number, percent, quantity, milk that I want to actually tag. I have sentences, so these are all the sentences that I want to do it. If anyone's played with Alex, it's very similar, or Louis from Microsoft. So in this case, what is it? It is, so if I can go back to this intent, if I look at coffee, sorry, React, not my specialty. Go here, we can go and edit, and I'll show you what it looks like. Make me a coffee. So what this is really simply doing is that it's getting a sentence, we're just tagging it, and we get a CSV file. But we are able to then go, say, click on train module. So what this does is we, using Kubernetes, send the export JSON that has all the right tags to a Google Cloud instance, and it's at the moment training a machine learning model. What happens then is that model and its intermediate files with the ML model and the TensorFlow files are kept in a Google Cloud bucket. Once that's done, we're able to click on the iOS, and we get an iOS framework. But what I was going to do, can I actually do it? Maybe I can. That's my... I can't get the SSH, but I'll show you what I've done. This is like cooking, television cooking. I have a pre-made screen recording, and then I do phone, I think. Yeah, here we go. Okay, so what happens is that once you've trained the whole thing, oh, jeepers. Wait, no, microphone. What? Oh, right. File, new movie recording. Recursion. Here we go. So iPhone. So, so this is just the demo app that we built. And if given this thing and I type in the word, so here's some text that I wanted to classify. Make me a mocha with more milk. And this is not connected to any internet, but I'm able to go, all right, the drink that I want is mocha, quantity more, and what do I want? Milk, right? So you're able to, what you're able to do is you're able to then say, well, you know, I want to build a bot, and I want to build a bot to actually take free text input. I want you to classify this, and you know, you can go back with your rule-based thing and say, all right, if somebody said X, I want you to reply that. Say Y, reply that. Or if you didn't give me enough information, I should ask you, hey, would you like me to book a ticket for tomorrow or when, kind of thing. So yeah, hopefully this has given you a bit of insight on how you could do CoreML beyond the simple, hey, here's an inception model, go classify banana versus like an apple, which is what everyone, that was the first use case for that. Convolutional nets. Hot dog. Oh, hot dog. Hot dog or not hot dog? That's the one. And you know, explore how you can actually manipulate tensors to do the things that you wanted to do. So like, you know, this, I mean, technically the LSTM is also very good for speech recognition. So anything that's sequential based, you can use the LSTM for. So speech recognition, we've done it with handwriting recognition as well. We've done it with, yeah, we've done speech as well. But yeah, lots of different things. I think you can do accelerometer data. So given, you know, what the gyroscope and the accelerometer is doing, you can classify if someone's walking, running, you know, whatever. So there's a few ideas on how you can do it. Any questions, thoughts, comments, queries? Oh yeah, one more thing. I am writing a CoreML book, so if anyone has any ideas or would like to know, or would like to, you know, have, you know, mentioned, I would appreciate feedback. It's a very weird space because I don't really know what to write, because I could write it very machine learning heavy and then everyone go, but this is an iOS CoreML book. Or I could write very much CoreML stuff, then I wouldn't really have much machine learning to write. So I kind of need to balance that out. All right, questions? Yep.
Yeah, so segue into that. So apologies if you've already covered this, but a couple this is doubled up in terms of machine learning and MultiRace. So how do you like you touched on it? You press the button and it trains it.
Yep.
Did you cover training and how you train a model and make use of it? Is that a bit useful?
Let me see. Do I have? So, let me go back to the keynote. So, what's really interesting is that this code here, it's a snippet from the training code. So in machine learning, the only difference between training and inference is that in inference, you don't do what's called the backpropagation, which is the error correction, right? So in a nutshell, what backpropagation does is it says, all right, I'm going to give you these weights. I want you to predict something. And then the algorithm will predict something, and it says, all right, your accuracy is 0.78, whatever your cost function is going to be. Given a cost function, and it has to be a differentiable equation, you can, using the chain rule, backpropagate using calculus the gradients. And because you have the gradients, and the gradients will point in a certain direction. Imagine if it's a topology map. It will point to a certain direction that says you need to walk in this direction to go down the hill. And the further down you get to that hill, the better your accuracy becomes. So I'm sorry I didn't really talk much about training, but if anyone's interested, I probably could talk again some other time about actual training a model. I think the guys at MLAI may also be doing that as well, so there might be a bit of overlap there. But yeah, pretty much in a nutshell, this is pretty much mostly training, and then in most frameworks, all you really have to do is in Keras, call the command model.fit with your data, and in PyTorch it'd be something about backprop or something like that. Yep.
Okay, so after bewildering us for half an hour.
Sorry.
Where
in a good way. In a good way.
Yeah, in a good way. Yeah, in a really good way.
That's coming from Oliver.
Where is the best place to start if you're interested in like learning more about machine learning and like actually because like you talk about like gradient descent models,
Yep.
and differential equations, and all the rest, and some of us, including myself, know the words but
Have not touched it in a long time.
and haven't done like real math in a very long time. But you know, beyond like basic vector mathematics or something crap is good. Yeah, where do you start if you have like an interest in like learning actually what's going on when you're training, or like you can follow tutorials and you're like, oh yeah, okay, you do this, and there's all these existing models and you can apply them.
Yep.
But it's still to me like whenever I hear people talk about machine learning and stuff, it just seems like this impenetrable pile of jargon and mathematics and stuff.
Yes.
Right.
Don't worry, I feel the same as well. Most of the time I go to the conferences and they pull out like, here's the KL divergence and blah, 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 and all this math thing. You just, you lose it. And to be frank, I think most machine learning practitioners are also the same. We try to hide behind a lot of math, but a lot of times they're like, I have no idea what this guy was on about. And then you usually have to sit there and read the paper like 6 times, and then you go, nah, I still don't get it kind of thing. Then you send an email, and then you say, hey, give me your data and your code. I mean, to be frank, like that's what it is. Machine learning is still very much voodoo magic. A lot of the times you do, we did this, and I had no idea whether it was going to work. Like, unlike programming, software engineering, when you go put XYZ code, you're going to build like a bridge. You're going to build something. In machine learning, you have no idea if what you're putting together is going to get you something. The only way to know is just to do it. And there are no real hard and fast rules why things work. And if it works, you just document it and write a paper and say, I did this and it worked. So this field is extremely new, very raw. There's not much discipline, and people have been railing about it and saying, oh, how can you do that when you're putting it into a car that's driving itself? How do you know it's going to work? And we just go, it kind of works. Yeah, no one died yet. And so.
Well, they talk about the alignment problem in AI.
Yes.
Of like, you don't know whether or not you're building a paper that maximizes it.
Correct. So I think, it's very new, it's very interesting, not really ready for mission critical stuff. It's more like, hey, look, I have a dog face, or I'm vomiting rainbows kind of thing. You put it into those kind of apps, and people have fun with it. Yep.
Can you speak a little bit about why we should be maybe doing any of the, caring about having a model on the device versus doing all that stuff in the cloud and just using an API to go, look, I've got some data,
Yep.
Please give me the inference.
Yep. At the moment, not really. At the moment, that's probably the best way to do it. But going forward, I mean, the holy grail is robotics, right? Everyone's a robot. Everyone wants to follow you around, do stuff for you. And for that, we have to make robust AI, right? So you can't be continuously tethered to the cloud because, if you took your robot out to say...
You don't want your Tesla
yeah.
to be reliant on trying your 4G
Yeah.
when it's making a decision about whether or not to drive through.
I get that.
Yeah.
But as an app developer, I was trying to argue we should do it. The CoreML.
The people API was broken today, so we just reached everywhere.
Miles, it's when REA just drives you to the house that you need to buy.
Yeah.
Well, the cloud providers aren't doing it pro bono, right? You pay money for them to do stuff. Like, every time you give it an utterance and it does this, they charge you maybe 0.005 cents. But, if you have an app that completely explodes in the market and, you want to reap the rewards of that, but you can't because now you're paying so much cloud, compute fees, this is probably when it's really going to matter, right? Where you're running it on device and you don't have to rely on anybody. Because I hear that's the big problem with a lot of, indie devs. Back in the days when, we were able to sell an app in the App Store and profit from that, it was great, but then you had to keep supporting it, and then you had to run a back end, and then your back end costs money, and then you go, well, it's not really worth it anymore. Sorry, guys, I'm going to shut this thing all down. The more we are moved away from the cloud, the more we actually can do compute on device, the better it is for, I think, experience for our customers and also longevity of our applications. Because I think that, cloud is great, but cloud is also such a massive drain on indie devs, right? Because you have to factor it in. And then once you've sold your app, unless you have ads, which is a really bad experience, you're not going to be able to continuously, pay for that. So, it depends on your business model. Some people might like it, some people might not. If you work for maybe REA, then sure, do the cloud because they've got tons of money, right?
I think the other point, when you had a slide up at the beginning
Yep.
about why CoreML, why the edge
Yep.
versus the core, and as privacy is a big one, right?
Correct.
Every time you're sending, if I take a photo and I'm Instagram, I'm taking a photo and it sends it to the cloud and it classifies it as a cat or whatever it is, you're giving that information to someone, right? You're giving semantic information, right? At the moment, obviously people don't mind sharing their pictures of whatever to Instagram and Facebook, but if you actually cared more about your privacy, it's well, should I really be sharing all of that data about my life with some third party who's going to potentially apply machine learning techniques to it all to figure out actually what I'm looking at all the time? At the moment, it's relying on the human to go, hashtag kitty cat. But if it can just go, well, we don't care what the human says, we can just do a classify based on our ML models.
Actually, that's a really good point as well. So if you look into detail with a lot of the ML models, ML services by the cloud providers, they are run on public instances because it's just too expensive for them to actually do anything special with them. So if you're in a sector that has high regulation, so like healthcare, finance, or government, it's very unlikely that you can actually use any ML models for that because the cloud providers will not sign off any BAAs or whatever else around it. So it makes a whole lot of sense to do this because actually one of the reasons why we did this was that we wanted to build our own models that we can run on device because we're in the healthcare space, and also because we have the same models, they also can be packaged up into a Docker image and deployed on Metal, right? On whatever internal servers that say the government has or a bank may have, because there is that information privacy sensitivity that comes with dealing with high regulatory industries.
Hon, just to clarify, the reason you had that sort of web interface and everything to do the training, besides the fact that you're sending the training and doing the training in the cloud, part of the reason you want to do that is because you need to be able to sort of code gen a certain amount of the client app to conform to the model.
Correct, yeah. So, I'll show you what it looks like. So,
if you didn't do that, you'd essentially just have to...
Yeah, every model you need...
either spit out the code as just template, copy, paste this into your app, or sort of do some... Just tell the user or the client here, these are the parameters you need.
Oh, sorry, I'm just realized I'm in Tether. So, no, exactly right. The only reason why we did that was that we wanted an automated process, right? Because otherwise, you can do this whole machine learning model. You say, all right, how many intents do you have? You have 3 of that. All right, I'm just going to modify my Objective-C or Swift code for 3, and I'm going to have a, vector size of 300. I'm going to modify that. But if you do this, you never really have to touch it again because, I didn't mention this in the talk, but in machine learning, what's really interesting is there are only 3 components, right? You have your model architecture, which usually doesn't change because once you find one and it works, you leave it as a side. You have your data, which is really important, and your cost function, right? Your cost function determines how accurate your model has trained or not. And usually also you don't change that. So the only variable that you change is that data, and that data is, what do I have in my sentences here? How many of them do I have? What do I tag them to be? And these are metadata, pieces of metadata that if you can capture that at this training time and apply it to your inference, then your CoreML model is sweet. You don't have to go, oh, what is the 6th neuron telling me about this particular thing?
Okay, so you're kind of saying, in CoreML world, once you set up those intents, for example, you can't, if you were doing this on your device, or just on your own machine, you couldn't really you can't change the intent set without retraining.
Yeah, exactly. Because the Keras will actually spit out. So in Keras, if I go back here, so what happens is that once you train Keras to do this and you test it and it really works very well, you save the model as a H5 file. And that H5 file is what's put into CoreML to generate the, this convert call in Python generates the ML model file. It does that blindly. It doesn't know what it is. It's just taking, it says, I'm going to take in none 300. I'm going to give you 6, and 6 is the output. But the problem is you don't know what 6 is. And I said the order is really important. 6 could be coffee, cereal, something, right? So if you capture that information at that start there and you put it in, you bypass the whole static compile of CoreML, in a sense. That's why we go back into templating world.
I think Oliver has a lot to learn.
Yeah.
We've got one more question at the back and we should
Right. So you mentioned the data there, how much data, that example there for the coffee intent, how many sentences or whatever, how much data do you actually do that?
This one had 48 sentences, but it varies. Again, the only way to know is to do it. That's really the mantra in machine learning. The reason why we're able to get 48 to work is we used a pre-trained word vector, fast text. The one that I was talking about, man to king, woman is to queen, because it's already captured a lot of semantic information about the world. So by it knowing a lot of the semantic information, it's able to make good guesses. So I don't think I mentioned any mocha in my training set. But because it sees the word mocha and it's very close in geometric distance to say the word coffee, it goes, well, it's most likely going to be a drink, so I'm just going to tag it as a drink. And this is the real power of these models, is that you don't necessarily have to give it every example. It should still be able to work on some things that it's never seen before just by the proximity of the words. And also, what's really interesting, we've done some really interesting experiments. We've done this in English. And then we took that and transplanted it with Chinese word vectors. And it actually works in Chinese. So you train it in one language, and then you're like, all right, I'm going to try a different word vector in Chinese, and it just spits out the correct answers. So we thought it was a bit freaky and kind of cool, but your mileage may vary depending on what kind of data sets you have and the topics.
So I think that's one of the key points you're making there, is that a lot of the power that people are getting from machine learning systems now, and things like TensorFlow and Keras and CoreML, is that academics have gone and done the hard yards and built things like ImageVec and WorkVec and stuff like that already that give you that sort of base brain. And you're just tweaking it.
Correct, yeah. So you're absolutely right. So in machine learning world, in statistics, we call that an a priori. So in Bayesian world, the researchers have given it a lot of understanding about what the world is. All we're doing is saying, all right, I want you to take that understanding, I want you to tweak it particularly for my use case. And it's able to do that.
Awesome.
Cool.
Thank you, Hon.
Thanks guys.